All right, thank you so much, everyone. So today's speaker is Ramesh Shah from Washington State University. He's from the Department of Computer Science. And Ramesh, the floor is yours. Go ahead.
Thank you for the introduction, Mustafa. I will now begin the presentation. So, okay, I need to rearrange some things. Oops. Let me try this one. You still have my screen, right? Okay.
Yes.
Yeah. So hello everyone. Thank you, Mustafa, for inviting me. Today I will give a talk about application of machine learning and embedded system in healthcare. So just to give you a personal background about me, my name is Ramesh and I am from Nepal. Nepal is a very beautiful country with highest mountain peaks in the world and also vast green valleys. And in terms of my education, I did my undergraduate in electronics engineering. And after that, in 2018, I came to the States to pursue a graduate education at Washington State University. And primarily for my interest, I love working with embedded systems and also machine learning. So machine learning has been a vision interest of mine. Previously, from my undergraduate years, I always loved working with electronics devices, making them work to do something, like program a robot, make it walk or follow along a line, those kind of stuff. And in my PhD, I try to use these two technologies, embedded system and machine learning, to address issues in healthcare. In terms of today's talk, this is the outline of our talk today. So first of all, I will briefly talk about embedded system and machine learning. I will just give an introduction to it just so that we have some idea about these two concepts. And then I will talk about my own research of using sensor system and machine learning in healthcare. So let's begin then. So first of all, I want to ask, what is an embedded system, right? So this is very important because we need to understand it before we can actually before I can actually talk about my own research. So if you follow, go on the Wikipedia, this is the definition you will get. So an embedded system is a computer processor that has some memory and some input-output channels and has some dedicated function within a large mechanical electronic system. So this is a very, I would say, complex definition. But embedded system, for what I understand of embedded system, is electronic device that has some computation functionality and are hidden from your direct view, the direct view of a user, but are very crucial to the operation of devices. For example, take your coffee maker. If you made coffee in the morning, you must have used one or not one, but a coffee maker has many different functions. You can set a timer, you can program it, you can even control the temperature of water in some sophisticated machines. So behind all of these functions, there is some processing happening inside, and that is exactly what embedded systems are. So embedded systems are everywhere around you. If you look around your room, you will find more than one of them for sure. Your smartphone is an embedded system. So this is embedded system. Embedded means that is inside. So any electronic device that has some computation capabilities, some logic to it, but is hidden from the view, is an example of embedded system. And with that, I don't work in general with embedded system because there are many different kinds of embedded systems. The kind that I'm interested in is called sensor systems. So a sensor system has sensors in it. And sensors are devices, mechanical or electronics in nature, that measure some physical quantity. For example, you can use you can use the principle of resistance from electricity, the Ohm's law, if you remember, to actually measure the intensity of light in the room. So that is one kind of sensing, one type of sensor that actually measures the intensity of light. There are many other different kinds of sensors, for example, heart rate sensors that can measure the skin conductance, the conductance on your skin. Sensors that can measure humidity, geomagnetic forces, and much more. And sensor systems have sensors in them and also some control circuits to actually operate these sensors and read the values or read the observation of the sensors. So sensor system is a type of embedded system that has sensors to measure some physical quantity that is present in the environment, and then get the data from the sensors and also control the sensors. So basically, sensor system allows us to measure physical phenomena and express the measurement in meaningful ways. Right? And there are many different applications and I would say benefits of sensor system. And one of the benefits that I'm going to talk about is from healthcare. There are many other different kinds of benefits. For example, your automation, if you can use, Alexa and Google to do whatnot today. And all of those is an example of sensor system. So there is a microphone in these devices that is actually sensing your voice. And machine learning is happening behind the scene to actually recognize what you're saying. And then you can, turn off your light or turn on your light and do many different kinds of, that is an example of automation. There are examples in monitoring, even in education, right? So in general, sensor systems are very useful because it allows us to actually measure something, some processes in the real world, and then use that measurement toward any application or any object. So that's why I'm interested in sensor systems, because it drives, from my perspective, I think it drives building of new things, right? So at my core, I'm an engineer. I like to build things. And that's one way sensor system allows me to build different kinds of things. So to recap, we have these embedded systems that are everywhere. And within the embedded system, within the spectrum of embedded system, there are these small devices called sensor systems. And the difference between the embedded system, one crucial properties of a sensor system is that these systems are very small in their physical dimensions, right? So that you can fit it in many different places. Now with that, I will move on to machine learning. So now I will just talk briefly about machine learning, just to give you an idea about what machine learning is, rather than going into details about many different facets of machine learning. So if you would ask me what machine learning is, I would say that machine learning is a process of learning pattern in the data to associate variables to some outcomes. Right? For example, if we take this figure here, for a human, we can clearly see there are two different classes here. Right? One is the classes of circle, which has a color of blue, and the classes of triangles that has red color. And for machine learning algorithms, from the perspective of these algorithms, we can the attributes of these two different shapes, the radius or position in space, or any other attributes that are geometric in nature, could be thought as variables, the x values, right? And the color of these shapes can be thought of as outcomes or labels, the y values. And the machine learning is about finding a decision boundary so that whenever there is a new input, we can assign the output to these new inputs. Machine learning actually, for me, what I understand about machine learning is the process of using the attributes of variables to learn function so that we can find a value of a new input x. The value will be f of x. Right? So machine learning is about finding the pattern or finding the function. And with that, I also want to make a distinction between machine learning and artificial intelligence, because nowadays there is a lot of buzz around these terms like machine learning and artificial intelligence, and most of the time one term is used interchangeably with other term. But there is a, I would say, a big difference between machine learning and artificial intelligence. Um, Artificial intelligence in general is a sub branch or a subfield of computer science that is concerned about with developing, agents or systems, a machine per se that has intelligence very akin to what our intelligence is. And our intelligence, the human intelligence, is what is called general intelligence, right? But machine learning, which is a component of artificial intelligence, it's much more focused about learning models or developing systems that has very narrow or specific intelligence, right? When I say narrow and specific, I mean machine learning systems are most of the time trained for just one task, and even for that particular task, it is not they are not competent, like they don't perform at the same level for many for all the different scenarios of that particular task, right? For example, if you take the self-driving car, like your Teslas, they can drive very well on the roads of San Francisco, right? So the task is about driving, and they are very good at it on the roads of San Francisco. But if you change the environment, for example, if you take them to the roads of Kathmandu, Nepal, then they won't be able to drive that efficiently or that properly, right? So even though these systems are good, they are not intelligent, or they don't have, broader level of intelligence. So machine learning is focused on developing these systems which are very narrow intelligence. The artificial intelligence is a general intelligence like a human, which can drive a car anywhere in the world or even on Mars. Right? So that is the difference between machine learning and artificial intelligence. And with that, let's move on to different kinds of machine learning approaches. So how we train these very narrow and specific intelligence system, right? So there are three different types. The first is supervised learning. And in supervised learning, we have both the values of x and y's to learn the decision from, right? So it is called supervised because we also know the values of y, right? So given x, we also know the value of y, and then we try to find the function f, which is represented by this purple line here. In unsupervised learning, we don't have the y value. We just have the values of x's, right? But nonetheless, we try to find the decision boundary. And there are different approaches in both of these, different methods in both of these learning paradigms, supervised and unsupervised, that allows us to do so. I will not go into details about them. I just want to introduce you to these different learning approaches. And the third learning approach that is also important is called reinforcement learning. Reinforcement learning is very similar to how we human or even intelligent being actually learn. For example, consider the case of you trying to make your dog learn how to fetch a stick, right? So the dog actually observes you in the environment, throw the stick, and telling it to go and fetch it, right? And if it brings the stick back, then you will reward it, maybe give it a pat or food. Right? But if it does not bring the stick back, then you keep on trying. So you are changing more things in the environment. So reinforcement learning is basically that. There is an agent which actually observes the changes in the environment, and the agent is trying to do some actions. And based on the changes in the environment, the agent tries to do that action, and the reward function is implemented so that positive and both negative learning is handled or reinforced, so that the agent is steered toward doing the task that it is that we're trying it to learn. So reinforcement learning is very similar to how we learn, by observation, by reading, by watching, those kind of things. But in this talk, I will just talk about supervised learning because that is the technique that I mostly use in my own work. So to recap, machine learning is about finding pattern in the data or learning the function given the value of X and Y, supervised learning. And there is a difference between artificial intelligence and machine learning. Now, with that, we have a background in both embedded systems and machine learning, right? So now I will talk about my own research, and my research is about using these two different technologies, sensor systems and machine learning, to address issues in healthcare. And two such issues that I am involved in, that I work in and I'm working on, the first is trying to determine association between stress and alcohol relapse. And the second is understanding complex physical and behavioral events in uncontrolled environment. I'll talk about both of these projects. I'll talk about stress and alcohol relapse in more detail because we are actually at the end of that project. And for the second one, we are just started. But I just wanted to give you an idea what the project is about and what we can do using embedded systems and machine learning, and to what end, right? What are the objectives? So first of all, let me talk about the stress and alcohol relapse, right? Just and to establish the importance of the problem, alcohol addiction is a very serious public health issue, and that this must be a known fact to many of us. And just to give you a number, more than 50 million people in the United States suffer from alcohol addiction. And furthermore, stress detection and intervention is actually considered a key element toward preventing alcohol relapse. So someone who is trying to remain abstinent from alcohol, uh, if, if he or she goes through some stressful situation, then the chances of relapsing actually increases. So the goal of our study was to study the effect stress and stressful events on alcohol cravings and relapse. So given a person who is addicted to alcohol and who is trying to remain abstinent, we wanted to study how stress and stressful events affects the person craving and also the chances of relapse. Right? To do that, we did a study and we collected data. And I will just list out some components of our study here. So we collected physiological data and also some survey data from individuals who were actually suffering from alcohol use disorder and were trying to remain abstinent for 12 consecutive days. Right? For 12 days, they were under observation, not in a lab, in their own home, but they were the empathic E4 wristband that is shown on your right here, which has many different sensors, and they also responded to surveys on their smartphones, and they checked in regularly at regular intervals for their meetings. In terms of the biomarkers, we collected data about heart rate, skin conductance, and skin conductance is basically how good your skin surface is for the transfer of electrical charge, right? And it is skin conductance is considered a very good measure of stress because the phenomena of sweating happens when people are usually under stress, and when sweating happens, the skin conductance actually increases, right? So with other variable in constant, skin conductance is very linearly correlated with stress. That's why we call it skin conductance, and most of the analysis is skin conductance. Among other data, we also collected skin temperature and also movement data, accelerometer data, using a device called Empatica E4 that can be worn on your wrist and like a smartwatch. But it is a bit bulkier than a smartwatch and not very sexy looking compared to say Apple Watch, right? And there was also the survey component. Well, the survey was 4 times a day, and I asked the participants about their emotional state, their mood, stressful events, and also their alcohol craving. And finally, we also conducted interviews at the beginning and then during the participation phase. And now I will move on to the results part. So here in this slide, I am showing you a graph that is taken from the EMS survey, which actually reports the reason behind stress. So we asked the participant about how, when they were stressed, and if they were stressed, why they were stressed. So as you can see, in daily lives, the reason behind the stress can be many different types, right? Many different types of reasons. And most of the time it was something they started thinking about and they feel stress. And if there was, and the other prominent reason was conflict with others. So this goes to show that, in daily lives, most of the time, these uh, people who are particularly vulnerable, they are under a lot of different kinds of stimuli, and stress is a very prominent, prominent component of their life. And the reasons behind their stress is very varied. For example, unsafe surrounding, money problems, um, health problems, legal problems. All of these social problems actually originates from the original problem of health, right? Original problem of addiction. So all of these are correlated, and all of these actually contributes to the a stressful condition of a person. And also in the interview, we asked the participants about the general satisfaction of using a wearable device to actually measure the biomarkers. And we found that most of the participants were fine with wearing a wristband if it was designed to help them in some way. And some participant or even expressed that they actually felt relieved that there was some kind of device which is trying to make things better for them. So these observations that we found actually highlights the potential benefits of using a wearable device to assist individuals uh, suffering from addiction such as alcohol. And the next study that we did was to examine the correlation between cravings and stress. In this paper, we also studied the quality of the data that we examined the quality of the data that we collected, and we found that most of the data that we collected was good data, free from noise, and using the features, the statistical features that were computed from these sensor modalities, we computed correlation metrics for different measures, such as how stressed they felt, their cravings for alcohol, their mood, positive, negative, their discomfort and pain. As you can see, we found a very significant correlation between cravings, positive, negative moods, discomfort and pain. And in this paper, the aim of this paper was to study this correlation, to try to establish the fact on the ground level. And these correlation are experiment correlation coefficients. And results in this paper actually suggest, the real world assessment of stress using a wearable device is actually feasible, right? And can be used to develop mobile interventions, automatic mobile intervention, to help these people uh, to remain abstinent and sustain their recovery. And yeah, so the next result I'm going to talk about is a very recent paper that was accepted. So as you can see, the Empirica E4 has a lot of sensors, right? And Empirica E4 is a very expensive device, upward of $1,000. So it is not a very, it's not a device that is very that can be bought by everyone, a person that has very limited resources. And one way to actually bring down the cost of these systems is actually make them simpler. And one simplification is to decrease the number of sensors. So, and decreasing the number of sensors has other benefits as well. For example, less number of sensors means less power draw from the battery. So the device will last long, right? And that is another benefit. So in this paper, we wanted to study what is the best modality, best sensor modality to actually measure, to actually detect the stress. And towards that, we implemented some machine learning algorithms, some linear models and some nonlinear models towards the task of stress classification using data from both several modalities, all of these modalities, and just one modality. What we found was that the model trained on single modality was comparable or even better sometimes sometimes during our cross validation on the models that was trained in all these different four modalities. So here we have four different sensing modality. The first is acceleration. The second is blood volume pulse, basically measuring the movement of blood in uh, your veins. So this is related to heart rate, but it is a much more basic level of measure than heart rate. So heart rate is actually computed using blood volume pulse. And EDA is your skin conductance, and temperature is your skin temperature. So as you can see, there is hope, or there is a model that is just training one sensor modality can be used or is comparable to all a very complex model with input from many models. So this goes to show that we can design simpler systems that will be less costly and cost efficient and can be used in daily lives towards detecting stress and doing intervention, which is the ultimate goal of our product. And finally, so until now, I have been establishing different facts, different reason behind our product. And the final task is to actually do stress classification. And for that, we chose not a very complex model. It's a very simple convolutional neural net with just few layers. We trained the model on just EDA data, and this is the results that we got. So on both the training and testing set, and both the F1 score and accuracy, we have more than 95% success rate on both the training and testing set with just the EDA data, with a very simple model. And the reason behind choosing a simple model is that a simpler model is easier to be implemented on the device itself, on the embedded system, so that it can run in real time. The inference time of this model needs to be very small, so that everything happens in real time. And the model needs to be small in size so that it can fit on the limited memory resources that are present in these embedded systems. So in these embedded systems, your smartwatch or off-the-shelf smart device that you design to detect stress, these are embedded systems. They don't have a large, very complex processor or very large memory storage. So that is also, we also need to take that into account when we are talking about embedded system or sensor systems. So yeah, that's why we chose a very simple model. We have not yet implemented these models on the actual hardware, but that is the ultimate goal of our project. Next interesting result that I also want to touch upon is on personalization of stress models, right? So as all of us are familiar, stress is very subjective. Same kind of a stimuli can be stressful to you, but not as stressful to me, right? For example, take riding a bike. Right? So if you riding a bike could be very stressful for someone who hasn't ridden a bike before, or has some other kind of fear, but not very stressful for another person who has already ridden a bike, has learned to ride a bike, right? So the same kind of the same stimuli can have varying effect on different individuals. And the reason behind this observation that I'm explaining is that the model that we train on this for stress classification on the sensor data uh, may need also be personalized or fine-tuned for each individual user, right? Because each individual user has varying characteristics of their emotional, their cognitive, and many other properties. So this is the graph here. This graph here is from our analysis on what is called leave one subject out analysis. So in that process, what we do is that we, in the training set, all the data from one subject, except from one subject, is in the training set, and the data from just one subject is in the test. So in the x-axis, we have these indicated for different subjects, and it means that For these subjects, the data were in the testing set, right? And for all other subjects, the data was in the training set. For example, if you take the first bars for S2, it means that the training set had data from all the subjects from S2. Yeah, so S3 to S17, right? But the test set has only data from S2. So here it shows that, on the training set, the model is performing good, but on the test set, the model performance actually dropped. And similarly, there are other subjects where the drop is even significant. For example, subject 14. So these observations actually, I believe, leads to the fact that, stress is very personalized in nature. So that this is what I believe what these observations or these results are telling us. And to actually test out whether we can personalize the trained stress model, we retrain. So there is a process called online learning where while the machine learning model is in use, we retrain the model on the new label data. So let's take the case of S2 here. So initially the performance of the model was 76.8%, but if we retrain the model on the data from subject S2, we can reach up to 96%. That is a huge improvement in terms of classification performance. So personalizing a stress model actually makes sense and may also be needed when these systems are actually deployed in real life settings. This is one more facet that we discovered in our study. And bringing all of this together, this is the whole overarching aim of our study. So we have these sensor systems, our smartphone, our wearable device that is used to collect data. And the data is used to do machine learning, context recognition, and generate personalized interventions for the user so that we can drive sustained behavior change. And so this sustained behavior change could be, in our case, trying to help an individual remain abstinence from alcohol. And it can be ported to many other domains. For example, sustained behavior change could be trying to make sure that a person takes his medication on time every day, right? And there are many more applications in healthcare, particularly in health. So any questions until now?
So I have a question on like your data set, the survey. So for how long did you collect data?
The data was collected for 12 days. So each participant, there was a 12 days period. And the survey was 4 times a day, and it was facilitated on my smartphone. It was an automatic process. They get a notification on their smartphone and they respond to the questions.
And the survey, you have only 5 or 6 questions, right? Is that true?
Can you please repeat that? I didn't get that.
On the survey, how many questions did you have on the survey? 6 questions?
No, not 6 questions. I believe it was upward of 10 questions.
Okay.
And the survey was facilitated at exact time. The time was fixed, for each of these 4 surveys. One of them was 9 a.m. The other was, I believe, 1 p.m. and likewise. And the questions were also fixed. But there were definitely more than 6 questions. I don't recall exactly how many, but definitely more than 6 questions. Okay, so I will move on to the next part. So the next study that I want to discuss that I'm currently working on, it's very in the beginning stages. It can be summarized in one sentence, that is human in the loop system, right? So these machine learning systems that I have been talking about, not very complex, but again requires data, and the data needs to be labeled, right? And labeling data can be very expensive in settings such as healthcare, because you don't the importance of labels is the importance of label, I would say, is much more in healthcare setting, which is very sensitive. It could be a matter of life and death in most of the time. makes the data labeling process expensive and also complicated. And one approach to actually address the problem of expensive data labeling is what is called active learning. So active learning is a process in which, uh, as the system is being used, the data is also labeled by the help of the user, and the model is retrained so that it is made better over time. So this sounds good, but there are some other complications in active learning. The first one is the burden on the user. Right? Imagine a scenario where you are using a device that you bought for you know to monitor your stress, for example. But the device is asking a lot of feedback from you instead of instead of actually helping you more often, right? So that is a burden on the user, and that can actually drive lower adoption rate uh, from the perspective of the device. And active learning, which does not recognize these physical and cognitive constraint of the user or the cognitive condition of the user, actually places burden towards the whole process of active learning. So that this actually can affect negatively on the whole idea of doing active learning and collecting data while the system is being used from the user, right? So we need to take these limitations or these conditions into account while doing active learning. The other challenge is the labels that the user expressed, uh, the end user expressed exhibits both temporal and spatial variations. And these variations, the model trained on these noisy data will be a poor model on the task that we are trying to uh, solve. When I say temporal, the phenomena of forgetting comes to mind. For example, most of the things that are not very important to us, we tend to forget over time. Right? If you were doing something, right? Maybe you were reading, you were sitting and you were reading a book. But if I ask you about the event, about what you were doing at that time, maybe 2 days after, and you might not actually you might not be able to tell me tell the system very confidently what you were doing, right? So these temporal and spatial variations actually results in poor labels, and poor labels mean poor models. So the whole objective of doing actual active learning is I would say is not very justified without considering these two different challenges. And that's exactly what we are trying to do in our current project. So we are designing a system. We are designing a system that has a human in the loop that makes the active learning, right, that collects sensor data in real time and real world setting. We're trying to maximize the active learning performance by taking the informativeness of the sensor data into account, the burden of the data labeling on the user into account, and also determining the reliability of the labels that we get from the user. So we are considering all of these three different facets while trying to do active learning. And our goal is to ultimately design algorithms to infer complex human behaviors. Right? So this is the whole, I would say, the whole over picture of this project. So we are right now in very early stages. So we are developing an app to actually collect data. We are developing an embedded system which has a camera, which will collect contextual data, and we'll use this data to actually query user or prompts user uh, to ask them questions. And all of this prompting, all of this query will be a smart model that will try to minimize the burden, try to extract more information from each questions that we ask, and also try to find labels which are reliable, right? And try to validate the labels in multiple ways. This is the overarching goal of the Women in the Loop project that I'm working on. This is very early stage, so I don't have any results yet. I just wanted to give you an overview so that you can get a context of healthcare that is a bit different, that is much more close to computer science uh, and, and also interesting. And before I conclude my talk, I also want to leave some thoughts, some breadcrumbs. So in terms of application of machine learning in healthcare, there are many different types. And for me, I believe there are three different types of systems comes to mind. First is diagnostic systems. And by diagnostic systems, I mean system that is actually helping the clinician to make towards diagnosing some ailment. For example, cancer detection. There are many research out there which actually promises to have built a system that can detect early cancer, right? The second type I think is assistive system. For example, sleep monitoring, stress detection. This kind of system can assist the user or an individual toward having a healthier lifestyle. Preventive systems that can prevent some things from happening early on, from early on. For example, early detection of disease, early detection of any ailment. Um, so many different kinds. So these are the three different avenues that I see in healthcare that machine learning can actually help. And machine learning is able to help us because the data that we collect in these settings, without these tools, without machine learning algorithms, it's very hard to make sense of the data, to actually use it toward an end. Right? So machine learning algorithms helps us to make sense of the data, to actually extract the pattern that we cannot see, us human cannot actually see or cannot actually glean without a very complex analysis. That's where machine learning comes in, and that's the purpose of machine learning to me. Right? That's why I'm using machine learning and how machine learning is used in my own research. And one problem of these machine learning systems that I also wanted to talk about is that these machine learning systems, like I said, has very narrow intelligence. Right? For example, the self-driving car, very good at San Francisco, not very good at some other place. Right? The same thing happens for machine learning system designed for healthcare as well, and the penalty is much more higher for healthcare system because this system can be life or death in most of the scenarios. The self-driving car is also the example of that, but it is not very intense in that matter. Machine learning system in healthcare, it needs to be very robust, very effective, very accurate, so that it can be used. And also, it needs to be exclusive enough. It should be able to consider all different facets of humans or any other beings, because we as a human have many different characteristics, right? So that is, I believe, a bigger challenge of using this machine learning system that we are trying to build in real life, to make them robust enough, to make them inclusive enough, so that they work in, like, if I have to give a number, I would say 99% of the time, because nothing is perfect enough, right? So we need to have a system that is very good. So that is one challenge that I want to leave you. So these are more avenues that you can go and read about, just explore on your own. And this is an interesting field, interesting aspect of machine learning, because it is actually useful. If done right, this will be very useful, and it will help many people, help you and me immensely to live a better life. So yeah, with that, I would like to conclude the talk and uh, open the floor for any questions that you have.
Thank you so much. That was a great presentation. So do you have any question here? Michael, do you have any question? Yeah. Okay, thank you so much. Is there any question online? No. I have one question. I mean, that is not that. So I'm going to just ask about E4 sensors. Did you make or manufacture that? No.
No, we did not make those sensors. We did not make that device. It's a commercial device
Okay.
available from a company called Gadiga. It was actually interesting. The interesting thing about that company is that it is started. It was founded by a professor from MIT who was actually doing a stress research in late 90s. So that's why we actually chose it because it is an off-the-shelf system and it actually allows us to do the analysis of what we wanted to do.
And
And
the
it's a
second
very
question. The second question is about the very last slide that you were talking about, like diagnostic machine learning, like for cancer and COVID. So, do you have any suggestion for data set that? I mean, is any like new
oh,
data?
so in terms of data set, right now if you guys have heard of Kaggle, it's a big platform of hosted data. And there is also a service from Google that is called Google Datasets, where you can go and search for any different like data set, any term that you put. It's like a Google search, right? If you say cancer data set, breast cancer data set, you will find a bunch of links that can lead you to actual data. So that's that. And in terms of data, there are a lot out there right now because the field has progressed a lot. If you go and Google breast cancer papers, you'll find pages and pages of Google pages. So
All right.
a lot of there if anyone who is interested.
Thank you. Thank you so much. So I'm going to just stop recording.